Imagine sitting down to assemble a massive jigsaw puzzle. You have 500 scattered pieces on the table, but the box and the picture on the cover are completely missing. Individual shapes and colors exist as isolated data, but there is no logic for how to join them together into a coherent whole. This is exactly what happens to a novice encountering a new, complex subject. Before adult learners can process and memorize detailed facts, their brains require the big picture. In instructional design, a well-engineered curriculum outline serves as that box cover. If you skip building that blueprint, the learning process collapses before it even begins. Yet in both higher education and corporate training, we see a consistent paradox. Subject matter experts possess absolute mastery of their fields, but they frequently design overwhelming, ineffective training programs. When asked to build a course, this is what an expert typically produces. This image shows a standard curriculum outline, a flat, unprioritized vertical list of numbered topics lacking any hierarchy or workflow. Experts build outlines this way because their brains automatically supply the missing connections between topics. They default to a Wikipedia-style dump of information, assuming the underlying logic of the subject is as obvious to others as it is to them. To fix this blind spot, instructional designers rely on cognitive load theory. We use it to engineer course structures that explicitly accommodate the severe biological limits of a novice learner. The design of the outline dictates how much of the expert's knowledge the novice can actually absorb. We have to start with a rigid biological constraint. Human working memory, the mental scratchpad we use to process tasks in real time, is highly temporary, fatigues quickly, and is easily distracted. Every piece of new sensory information you encounter must successfully pass through this narrow bottleneck before it can be encoded into permanent long-term memory. When a novice is introduced to a brand new subject, they hit this bottleneck almost immediately. Look at this novice's mental state regarding storyboarding. The concepts exist purely as scattered text nodes, isolated data points with zero connections. Lacking a mental model, holding just one isolated term in working memory demands heavy processing power. Dumping large amounts of unstructured information into such a fragile, constrained system creates severe cognitive overload, resulting in a total failure to learn. In 1988, psychologist John Sweller published a scientific framework for measuring this mental effort, known as cognitive load theory. The theory identifies three distinct types of load. The first is intrinsic load. This is the inherent complexity of the subject matter itself, and you cannot simply remove it. Intrinsic load is driven by a metric called element interactivity. This measures how many logically related elements must be held and processed simultaneously to understand a specific concept. High element interactivity places a massive, unavoidable weight squarely on working memory. The second type is extraneous load, which is the artificial friction caused by how the information is presented. It happens when designers use bad formatting, distracting visuals, or confusing rules that force the brain to waste processing power. As an instructional designer, your directive here is simple. Extraneous load must be aggressively minimized or completely eliminated to protect the learner's working memory. The third and final type is germane load. This is the productive mental effort and working memory resources dedicated to actually understanding the content, encoding it, and constructing permanent long-term memory patterns. Designing a curriculum is therefore a strict balancing equation. You must manage the intrinsic load, minimize the extraneous load, and maximize the germane load. Let's track how that germane load actually changes the brain over time, starting again with our novice learner and their scattered, isolated facts. As germane load is applied through study, the brain begins building structural connections between these disparate pieces of knowledge, creating what psychologists call a schema. This shows the intermediate stage, where a professional schema begins to form. Dashed lines anchor the outer concepts to the central task of storyboarding. Repeated practice thickens these pathways. The brain retrieves information faster, and connections become much stronger. Now look at the final stage of mastery. After years of experience, the expert's schema is a dense, deeply interconnected web where every concept links to multiple others. Because these pathways are permanent and automated, element interactivity feels incredibly low to the expert. They can draw massive, complex architectures into their working memory without experiencing any fatigue. This creates the subject matter expert trap. Because they no longer feel the heavy intrinsic load of the material, experts assume the connections between topics are universally obvious. This assumption leads them to write curricula by simply listing topics, failing to explicitly teach the underlying connections that the novice desperately needs. An expert's greatest asset, their densely woven, automated schema, is precisely the thing that renders them blind to the cognitive limits of a beginner. Fortunately, the human brain has a unique strength we can use to circumvent the working memory bottleneck: patterning. The brain naturally seeks out big-picture patterns to encode new information before it focuses on the granular details. To see this in action, let's compare the expert's unorganized topic list on the left with a properly patterned outline on the right. Look at the reworked design. It abandons the abstract list entirely. The top horizontal bar establishes a linear workflow. Isolated facts are declarative knowledge, while actionable steps are procedural knowledge. By organizing around procedural knowledge, we provide a natural, logical pattern. The declarative knowledge, all those isolated theories and facts, is now safely nested inside these procedural tasks, giving the facts immediate practical context. Task-based patterning translates a chaotic pile of facts into a navigable roadmap. It gives working memory a safe, predictable path. This task-driven outline is a perfect execution of the cognitive load balancing equation. First, it manages intrinsic load by chunking workflows into discrete steps. Second, it minimizes extraneous load. The structured grid and headers remove guesswork, freeing mental processing power. Finally, it maximizes germane load, forcing learners to connect abstract theories directly to real-world outputs. A professional outline ensures every lesson remains anchored to the primary learning outcome. An effective outline is a piece of engineered cognitive scaffolding, specific